example 7.5 or 8.5 for the given textbooks. For details, please see the description below. Steam enters an adiabatic turbine at 5 megapascals and 450 Celsius and leaves at a pressure of 1.4 megapascals. Determine the work of the turbine per unit mass of steam if the process is reversible. In order to calculate the amount of work of the turbine, we need to do a balance of energy on this turbine. We have that the rate of energy in minus the rate of energy out is equal to the change of energy in the system. Since we consider this to be a steady process, this value is going to be equal to 0. Then we have that the rate of energy in is equal to the rate of energy out. In a turbine, the quantity that goes in is the energy that is being carried by the fluid, which is equal to mass flow rate times the enthalpy at the entrance, and the amount of energy, the rate of energy leaving, is the power that is created plus the amount of energy carried by the fluid. Solving this equation for the amount of power, we have that the power out is equal to the mass flow rate, enthalpy at the entrance minus enthalpy at the exit, and knowing that the amount of power is equal to the mass flow rate times the amount of work per unit mass, we simply have this equation, and the mass flow rate cancels in both sides. Therefore, what we're solving for is the work per unit mass, and that is simply the difference between the specific enthalpy between entrance and exit. At state 1, we have the value of the pressure and the temperature, as well as the phase. It indicates that it's a steam, therefore we're going to assume that it's a superheated vapor. Therefore, we go to table A6 to get the rest of the properties. We go to 5 megapascals and 450 Celsius, and we find that the value for the enthalpy is equal to 3317.2 kilojoules per kilograms, and the value for the entropy is 6.8210 kilojoules kilograms Kelvin. So for state 1, these are the values that we obtained from the table. For state 2, we have a final pressure of 1.4 megapascals, and it also indicates that the process is reversible. Therefore, the value for the final entropy is equal to the initial value for the entropy, and that is equal to 6.8210 kilojoules kilograms Kelvin. Now we need to determine the phase at state 2. So we go to table A5, and we have a pressure of 1400 kilopascals, and we go and look at the value that we have for entropy. Our current value for entropy is 6.8210, which is larger than the saturated vapor, indicating that the fluid is still a superheated vapor. Since it is a superheated vapor, we go to table A6 for a pressure of 1.4 megapascals. We see that the value of entropy that we have, which is 6.8210, lies between these two values, which correspond to a temperature between 250 and 300 Celsius. We're going to interpolate between these two values so we could find the temperature and the value of enthalpy at this particular these are the values that we got from the table. By interpolating, we find that the value at T2 is equal to 267.5 Celsius, and the value for the enthalpy is equal to 2967.4 kilojoules per kilogram. Now that we have the initial and the final value for enthalpies, we could find the amount of work per unit mass. So once again, using the formula, it's going to be the difference between the initial and the final values of specific enthalpy. And we have 3317.2 minus 2967.4. Both of these are in kilojoules per kilogram. Therefore, the final value that we got is 349.8 kilojoules per kilogram. This is the TS diagram for this process. Notice that we have point 1 and point 2 aligned vertically since they have the same value of entropy. The lines that are drawn for each of the stages are a constant pressure, and we go from a state 1 of 5 megapascal to a state 2 of 1.4 megapascal. Both of the states have a fluid which is conserved as a superheated vapor. And notice that in this case, we are going to have an isentropic expansion.